This UCSD TV program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest programs.
This lecture series is in honor of my father, who did pioneering work on the rise in carbon dioxide that really set in motion the discussions about the science of climate change and onto policy questions. And this lecture series is really to try to bring in notable speakers who can talk to some aspect of that legacy. The legacy, somewhat unfortunately, continues to broaden with time. And touches on policy, it touches on the science itself. At one point we had someone in here, you may remember, who was you would have to say was an activist. So it's been a kind of a diverse series. Anyway, this time I'm very, very pleased to bring in Dr. Clara Desser from the National Center of Atmospheric Research. She's a senior scientist there, and she heads up the climate analysis section. She's been there since about 1997. Her background included an undergraduate degree from the Massachusetts Institute of Technology, and then she did her graduate work, at this point moving into meteorology, at the University of Washington under a very distinguished climate scientist named John Wallace. Her work is interesting. She touches on a topic that I think anyone who's thought about climate change has had to grapple with in their own life, and that's how does this narrative about rising greenhouse gases and the whole planet somehow moving towards a warmer state relate to what you experience as an individual through the course of your life? Because you experience changes, and are these changes somehow related to this larger picture, or is it something else going on? And in fact, it's a very complicated topic. It's a topic that really is at the cutting edge of a lot of research questions. And she's moved right into this arena. It touches on questions like what is the impact of Arctic ice loss on weather patterns at lower latitudes? How does global warming relate to El Nino phenomenon and these other changes that affect our climate for periods of decades or more that don't have anything necessarily to do with greenhouse gases? So it's a really important topic, and I'm sure there'll be questions afterwards. You know, Clara's a very humble person, as you'll see, and she's working on really neat aspects of this. But you can't be an expert on everything here, and so I encourage you to ask questions even if she can't answer them, because we'll want to see how she handles them. I'm sure you'll think of them as they go along, because it's that kind of science. So I want to say something else about her science. It sort of shares in common with my father. My father really stuck to the details, but he worked on science related to climate change that was very accessible to the public. It was a simple message. And Clara is that kind of scientist. She has stuck to the bench. She has really worked on the details. She stayed with some complicated narratives. But she hasn't lost sight of the simple, bigger questions. And I think you'll appreciate that in her talk, that these are difficult problems. They're not always clean answers, but the questions are clear, and you can see the progress going on. I'm very, very pleased to introduce Dr. Clara Desser.
I would like to thank the Keeling family, Louise and Ralph. I'd like to thank Cheryl and Margaret Leinen for the invitation to give this talk to you today. So Charles David Keeling was an enormously influential climate scientist. He had the scientific vision, technical expertise, and attention to detail and perseverance that has produced this unique and iconic record of climate change, the buildup of carbon dioxide in the atmosphere. This is a cornerstone of climate research. So I only had one opportunity to meet Dr. Keeling, but about 10 years before that meeting, I actually met his instrument. I was a graduate student at the University of Washington in the 1980s, and my topic was El Nino, and I sat mainly in front of the computer analyzing other people's data. And I wanted very much to go to the Pacific Ocean, to the site of El Nino phenomenon. And so I went on a research cruise for 5 weeks to do measurements and help to deploy buoys in the equatorial Pacific. And after 5 weeks on the ocean, we landed in Hawaii. And it took me a few days to get my land legs back. And the first thing I did was to make a pilgrimage to Mauna Loa to see the carbon dioxide instrument that was taking this fascinating record. So that was my pilgrimage to really Dr. Keeling's enormously influential work. I'd like to say 2 more anecdotes about my intersection with Dr. Keeling. About a decade after going to the observatory, I then came to Scripps as a young scientist to visit and give a seminar. And I remember, I was a nobody, and Dr. Keeling took me into his office, and he was enthusiastically wanted to show me some connections he had been discovering between the carbon dioxide record and El Nino events. And what I remember most from that was his absolutely infectious enthusiasm about the science, and then also the willingness to share it with a young person just coming into the field. And that has always stuck with me as a really important, although brief, encounter that I had with him. And then the third personal anecdote that I'd like to tell you is, unbeknownst to me as the years went by, I then realized that I had a kind of small world family connection to the Keeling family. And it turned out that my son and Dr. Keeling's granddaughter both grew up and went to the same preschool, took cello lessons together. I was the accompanist for the cello students, and so was Emily Keeling, Dr. Keeling's daughter. And by the time our 2 kids reached high school, the music had gotten too difficult for me to play. And my son asked Emily Keeling, Dr. Keeling's daughter, to accompany him for his senior recital. So it's a small world, and the love of music, my love of music, and I understand Dr. Keeling's as well, would have been another, I think, really nice common ground and connection if I had been able to tell him in person. I would have loved to do that. Okay. So I'd like to just tell you briefly about myself and where I work. I'm a scientist at the National Center for Atmospheric Research. I would say it rivals your view outside. It's just a different view, but I think we're both incredibly lucky where we live and work. As Ralph said, I've been a scientist there since 1997. The National Center for Atmospheric Research is a unique facility in the nation. It is, we have about 500 staff scientists or staff, but mainly we are a center for the university research community. And we house and build one of the world-class climate models, and I'll tell you a bit about that as I go through the talk. We also have aircraft facilities, which are the university community makes use of in their field campaigns. And then we have a very vigorous young scientist program. We have many educational events at NCAR. And one other fact about NCAR, it's in altitude about halfway between sea level here and the altitude of the Mauna Loa Observatory. So about 5,000 feet. And then I'd just like to thank for some key people here who have contributed to some of the work that I'll show you today, in particular colleagues from NCAR, Adam Phillips, Laurent Terret, and Jeff Keel, and then also Marianne Schaefer and the Resonance Chorus of Boulder, and you might wonder what that's doing here. It's actually a very important piece of what's here. I belong to this chorus. We are a group of about 100 singers, and this past season, our theme for our music was climate change and our emotional response to climate change. How do we, in the arts, how do we confront and process the enormity of climate change? And I decided that I would. I planned a panel presentation for this chorus of mainly artists and writers, very few scientists in the group. And some of the slides that you'll see really come from that presentation. So I think they're a very important part of the talk today. Okay, so turning to my topic, I'm going to speak about the causes of climate change, both in the past, climate change that we may have lived through, and also the future, what is coming in the next decades and centuries. So causes of climate change, I like to think of it as a balance, a scale here. And on the one side, we have the human component, what we are doing to influence climate. And then on the other side, we have a lot of the natural variability in the climate system. And these two coexist. That's the fundamental message that I have for you tonight. And the balance may tip as we go onto longer time horizons, maybe tip towards the human influence side. Or on the global scale, the human influence will become more and more important. But where we live, the local scale, it's much more difficult to say where we are on this balance. And one has to actually take into account that the natural variability may be playing an important role, at least at this stage. I want to emphasize that this message does not negate the science of global warming. I'm going to give you the underpinnings for global human-induced climate change, but just to say that on the local scale where we experience climate change, it's more nuanced, and it's a more complex picture to deal with. So when I speak about human and natural influences, I'm in particular speaking about, on the human side, the fossil fuel burning and deforestation. Those are the two primary ways in which we are influencing our climate system. And on the natural side, I will emphasize the internal variability that our chaotic climate system produces. Things like El Nino events, which you're all familiar with, being located here in Southern California, but also longer time scale variability, such as the Pacific Decadal Oscillation, which also has a strong impact on climate, particularly over North America. And in addition, on the natural side of the scale, we have volcanic eruptions, we have changes in solar output. These, of course, will also influence the climate. So here are some images from some recent climate events that have occurred in the past few years. Some of you may recognize Hurricane Sandy on the East Coast, the Boston snowstorms from this winter, California drought, wildfires, melting of Arctic sea ice. These are all catastrophic events. And the questions that we try to address and understand is, what is the underlying role of and importance of the human influence for these individual events, and what role did natural variability play? And again, it's a balance. It's not one or the other, but it is very much both influencing these events. So the outline of my talk, I have 3 chapters. The first is I want to go through the core scientific concepts that underpin the science of global change, global climate change. Then I'd like to move from the global view to the local view, as I just spoke about. And then finally, I'd like to talk about future projections, future changes in climate, and to emphasize that the science tells us that we should expect a range of outcomes due to the superposition of the natural variability on top of the human-induced climate change. So core concepts for human influence on climate. So firstly, I have five facts to tell you, and these are all the laws of physics, just like gravity. You cannot refute them. If you do, you pretty much give up on gravity. So firstly, this is the legacy of Dr. Keeling. This is the Mauna Loa record of carbon dioxide starting in 1958, when he was 31 years old, began this important set of measurements. It roughly spans my lifetime, which is amazing to me. And during that lifetime, carbon dioxide has increased 28%. And this increase, as I will show you, is almost entirely due to the burning of fossil fuels, to our energy use and activities. And in addition, you'll notice on this curve, in addition to the upward trend, of course, there are these little wiggles. And these are seasonal variations. And they have to do with the breathing of plants. So plants, of course, take in carbon dioxide, and they take it in during the growing season, which means they deplete it from the atmosphere. So during the growing season, the carbon dioxide content is declining in the air. And then during winter, the plants and the soils release that carbon dioxide back to the atmosphere, and it actually builds up again. So there's a beautiful seasonal variation also discovered by Dr. Keeling, in addition to this upward trend. So you might wonder, Mauna Loa in the subtropics, is this a special location, or do we see this buildup of greenhouse gases at other locations? Well, Scripps has been pioneering in this effort to collect the data from many different locations around the world, and I've just picked out a few of them to show you, all the way from the North Pole to the South Pole. Stations in Alaska, La Jolla, Hawaii, in the South Pacific, and then finally at the South Pole. All of them show a very similar upward upward increase in the carbon dioxide content. And then the second thing is that you really notice a very different seasonal variation at each location. So biggest at the far northern latitudes, where we have lots of plants, and almost non-existent at the South Pole, where there's very little vegetation to speak of. So this is a beautiful set of records, irrefutable that CO2 is going up. Now let me show you the longer perspective, which we can look at by combining together, splicing together the CO2 record from Mauna Loa with the long records from ice cores, in this case from Antarctica. So as snow falls onto the ice cap and the snow gets compressed, tiny air bubbles are trapped, and that air becomes basically fossilized, if you will. and tracks the amount of carbon dioxide that was present at that time. So people have gone and taken these ice core measurements and been able to measure the CO2 trapped in these air bubbles. And here I'm showing you a record for the last 2,000 years. And it's very, very steady until the beginning of the 20th century when it starts to rise. So if we look at this longer time span, there's actually been a 43% increase in carbon dioxide. Absolutely huge. Okay, number two, fact number two, this increase is due to human activity. This is some detective work that was very nice detective work to understand that this increase is arising from our human burning of fossil fuels. So just briefly, as I mentioned, plants, of course, take in carbon dioxide and photosynthesize using sunlight as their energy source. And plants have a preference for, most plants have a preference for the lighter isotope of carbon called carbon-12 compared to carbon-13. So that carbon-12 is stored in the plant. In this case, I'm showing you a tropical rainforest. And then as those trees get buried and get buried in swampland, turn into coal, and this is what we call fossil fuel, literally fossilized plants from millions of years ago. So this light isotope of carbon is present in this coal, and then when we combust the coal, when we burn it, that light isotope of carbon gets returned to the atmosphere. And these are measurements, in this case from Tasmania in the South Pacific, and it shows very clearly that relative to the heavy isotope, the lighter isotope of carbon has gone up. So this is a fingerprint that the carbon, the CO2 has come from the burning of the fossil fuels. And then one other very nice piece of evidence is the fact that, of course, we have to use oxygen when we burn, when we combust. And there are measurements of oxygen, in this case from the Scripps Pier right outside, and that is showing a decline in oxygen levels. Not enough that we have to worry about we're going to run out, but again, a very nice piece of evidence that this is indeed deriving from the burning of fossil fuels. Number three, carbon dioxide is an efficient greenhouse gas. So this has been known for a very long time, very well established in the 1850s using laboratory measurements with an apparatus pioneered by John Tyndall, and basically looking at the radiative effects of various gases. How much heat do they trap? This can be measured. And one of the gases that he tested was carbon dioxide, and it was very clear that this was a very efficient heat-trapping gas. So later, this was called the greenhouse effect. You don't need to read everything here. I'll just walk you through it. So the sun provides the energy to the climate system, and some of the sunlight, this radiation, is absorbed by the planet. And then the planet emits this radiation back to space in longer wavelengths. So these are the infrared wavelengths. And carbon dioxide is very good at absorbing those wavelengths of energy, and it re-emits that energy in all directions, including back down. And that's what's the heat-trapping aspect of this gas, is that it's able to re-radiate much of that back down to the earth. Water vapor is also a natural, very, very efficient greenhouse gas. And in fact, as carbon dioxide warms the atmosphere can hold more moisture, more water vapor is evaporated from the ocean, and that addition of water vapor doubles the warming just due to carbon dioxide alone. So this is a very powerful amplifier of the human greenhouse gas effect. So number four, greenhouse gases trap more energy in the climate system. I just showed you that. And this is evidence for that. This is the amount of heat measured in the oceans going down to 2 kilometers from a variety of different measurements. And they show a very clear increase over time. So this is measuring the energy in our climate system. The oceans cover 70% of the globe, and they contain almost all of the heat in our climate system. And then finally, according to the law of conservation of energy, this trapped greenhouse energy must warm the Earth. And here I'm showing you a map of the temperature change since 1950, and it's very clear that almost all regions have warmed. Some regions more than others. In particular, land areas in the northern hemisphere have warmed the most, as well as the Arctic. And so this is irrefutable logic and chain of events where we can go from Keeling's curve all the way to the warming of the planet. So of course, we call it global warming, but many, many other aspects of our climate system are changing. Snow cover, glaciers, sea level, all kinds of things are affected by global warming. In particular, very nice record of plants. The date at which certain kinds of flowering plants bloom on the East Coast. And without any exception, they're all blooming earlier and earlier as the climate warms up. We can look at the rate of sea level rise globally. These are some measurements from satellite altimetry data, where we have very accurate, precise measurements since 1993. And there's no doubt at all that the sea level is rising. If we look at a longer record, so the satellite record is shown here, and then these colored curves are showing you records from tide gauges around the world. And of course, these are a little more messy to deal with, obviously not global coverage, but all of the estimates show this roughly 10 inches of sea level rise since the late 1800s on a global basis. And then finally, a shift in the summer temperature extremes. So this is some work by Jim Hansen and colleagues. So in the 1950s, 60s, and 70s, we had a distribution of temperatures like this. And as we go through time, you can see by this most recent decade, compared to the green curve, which was the one in the 50s and through the 80s, we're now experiencing fewer cold days and more warm days. So the whole distribution is shifting over. It's not changing its shape, but it's shifting over. And as a result, it gives us more warm days at the expense of cold days. So that is the end of chapter 1. I'm going to move to chapter 2, and that is moving from the global scale to the local scale. This is where we all experience climate change, and I want to contrast for you the human influence and how to detect it on these two different scales. So let me begin with the global temperature record. This is the one that strings together all of the February data all the way back to 1880. And here we have the most recent February of this year. It was pretty much a record warmth as far back as these measurements go. So globally, this was, let's say, the warmest winter on record for the globe as a whole. So here's what it looked like in the US. And you all you know how warm your winter was. And this persisted not just for February. I could show you any of the months from this winter. Record warmth all along the western half of the country. And on the eastern side, especially where our national politicians sit, it was record cold. So again, globally averaged record warmth. In the country, it was pretty much a wash. So again, this shows you immediately the difficulty of being in one place and trying to deduce anything about the globe. So why did we have this pattern over the US that persisted this whole winter? Well, it had a lot to do with the path of the jet stream. And this is a picture for one of the days in February, but again, it was very persistent for the whole winter. And we had, here's the US, it's very hard to make out the outline, but we had this incredible sort of pocket of the jet stream coming down from the Arctic and bringing very, very cold air to the east coast of the US. And at the same time, California and the western states were under a very benign climate. As you all know, very little storm activity for you this winter. So the circulation of the atmosphere, the jet stream position, is very much what was behind this bipolar US for this last winter. So now let me put the US into the global perspective. So remember, once again, this is record warm for the globe as a whole, and the US is quite anomalous. So much of northern Eurasia was under record warm conditions, as was Africa and Australia. So a lot of warming that's what tipped the balance for the globe was occurring over the other continents. And then you can see kind of patches of blue and red, warm and cold over the oceans. It's a much more muted pattern over the oceans. And that's because the oceans just don't heat up and cool down as rapidly as the land surface does. It takes so much more energy to change the temperature of water than it does to change the temperature of air. So we'll always see much more muted changes over the ocean. So despite that the changes over the ocean are quite small compared to the changes over land, if you break down the global temperature record into the part for the ocean and into the part for land, it's very striking. The ocean time series shows almost a monotonic, steady increase over time. You can take any year and pretty much know where you're sitting in this long-term trend. In contrast, if you average all of the data over the land stations, yes, there's certainly an upward trend, but there's a lot more variability from year to year. And so even if you know a particular temperature for a particular year over land, you're not quite sure where you're sitting on this long-term trend. So these ocean measurements of heat content and sea surface temperature are crucial to monitoring the temperature of our planet. And of course, Scripps plays an enormous role in doing these measurements over the ocean. Okay, so now I want to talk to you a little bit more about natural influences on local climate. So very important to understand local climate because the global mean is made up of all the different locations and we're averaging across them. So we have to understand what's going on at the local scale. So I'd like to come back to this picture of the jet stream that I showed you a moment ago. And just to tell you that the atmospheric circulation is a very chaotic, highly nonlinear system. The phrase that we like to use is the butterfly effect. Dr. Lorenz, many decades ago, had the analogy that a butterfly flapping its wings in Costa Rica or wherever can determine the outcome of a particular winter in Boston, for example. So of course we can't predict when the butterfly is going to flap its wings, but the idea is that these are chance events, And because the atmospheric circulation is such a chaotic, dynamic fluid, these small chance events can amplify and grow with time. And we can never predict the position of the jet stream more than a few weeks from now at best. So we're always going to have this sort of chance nature of the wind patterns because of this, chaotic atmosphere that we have. So this really limits our ability to predict weather systems, also limits our ability to predict climate, which is the statistics of weather. So again, just to emphasize that the importance of jet streams and other aspects of the atmospheric circulation, they give rise to much of our local weather and climate variability. And they have very limited predictability. So being at Scripps, of course, a natural question is, well, what role do the oceans have on natural climate variability? And the answer is the oceans have a lot of influence, especially on longer time scales. So the ocean and the atmosphere interact with one another, and the ocean is a very sluggish fluid compared to the atmosphere. And so it contains sort of slower variations than the atmosphere, and it communicates those slower variations to the atmosphere and to our wind patterns. So even though the ocean has some more persistence and memory, it too is chaotic and nonlinear, and it still sort of has a limit on, again, how well we can predict changes in ocean currents, ocean temperatures, because again of this butterfly effect, that these are highly nonlinear systems, and small perturbations like a butterfly wing flapping can set the system off on a different path, and we'll never be able to predict that. So some examples of natural influences, natural phenomena that involve ocean-atmosphere interaction. I'm sure all of you are familiar with El Nino, and it looks like El Nino is building, finally, for this coming summer, and may have to do with how warm the water has been right off of Scripps, off of La Jolla here this past year. Then we have two other phenomena, one in the Pacific, which we call the decadal oscillation in quotes. Don't think of this as a pendulum. If it were, then we would have perfect predictability of this phenomenon, and that's far from the case. So it's best to think of this as variability that has a slower time scale, more like a decade or so. And then on the other side, in the Atlantic, we have a global ocean circulation driven by salt and heat contrasts. And this is called the thermohaline circulation. And this ocean circulation has very slow variations to it. And that's what we refer to as the Atlantic multidecadal oscillation in quotes. And it actually has a strong impact on climate in the eastern US, hurricanes, for example, and also over Europe. So let me just show you a little bit what these look like in the time series fashion. So this is the Atlantic multidecadal oscillation, a record of sea surface temperatures back to 1900. And you can see these swings that last for many, many decades. It's a remarkable record. I think Dr. Keeling would be very, very pleased to see something like this. And then we have the Pacific decadal oscillation, a similar character, but a somewhat faster variability. So the picture you need to have in your mind to really understand local climate is this schematic here, where we have the human influence acting inexorably, building through time, and then we have the natural variation that is superimposed, going up and down. And these natural fluctuations can have timescales of many decades. So you can be on an upswing of the natural or a downswing of the natural, and you may be confused about whether it has anything to do with global warming. But the idea is that they're both coexisting, and they superimpose to give us our climate. So let me show you some of my own work in this direction to try to tease out the component that is due to our natural variations in atmospheric circulation patterns, as well as phenomena such as the Pacific decadal variability. So this is the temperature changes observed over North America over the last 50 years. So this is a lifetime, or half of a lifetime, I should say, for many of you in the audience. And what we see is in wintertime, it has warmed substantially over the entire continent. And in particular, Western Canada has experienced the highest rate of warming over the last 50 years. So using some methods that I don't have time to go into, we've teased apart what is due to the natural variability and then subtracted that from the total to get what we identify as the human influence. And you can see that the natural component has actually contributed a lot to the warming in Western Canada. And indeed, if we put some numbers on it, about half of the warming, if you were sitting in a location such as, I don't know, Edmonton or something, you might think, wow, global warming is, very vigorous, and of course it's happening at the same time, but the natural variability just happened to augment the warming, or double the warming in this case. So finally, the last chapter before we end, and that is to talk about the future. And again, I'm going to draw on this concept of the balance, that we're going to have, even in the future, both a combination of the human influence and the natural. And of course, depending on the particular sequence of El Nino or Pacific decadal variability or Atlantic multi-decadal variability, we may get a different outcome locally from the part that is just due to the human-induced component. So let me spend a few words telling you about how the climate community comes together to make these climate projections. These are enormously important and complicated efforts. And some decades ago, the Intergovernmental Panel on Climate Change was created in 1988 to kind of bring together the international climate science community to really start to coordinate and understand what are the human components of climate change and what are the natural components. So many reports, many of us have contributed to these reports. Thousands of scientists worldwide. If I brought you my stack of reports, they'd probably come up to at least here. A lot of work has gone into this. So climate projections, these are done with sophisticated computer models of the climate system. These are based on the laws of physics. Of course, we don't have complete knowledge of all the components of the climate system. We try to model them as best we can, and of course we're always refining our estimates. But these are credible models of the Earth's climate system. And we test them, we make sure that they produce natural variations that are realistic. For example, the model has to produce El Nino events. It has to produce Pacific decadal variability. It doesn't have to do it at the same time as nature, because these events can occur at any time, but it has to produce the right statistics of the variability. So once our models are up to that task, we run experiments where we artificially increase the amount of carbon dioxide to these climate models. And then we also add this component of the natural chaotic part of the climate system. So again, we're addressing what are the future climate states given both the human component and the natural chaotic component. So let me just conclude with a few slides showing you some recent calculations from the model, the world-class model that is housed at the National Center for Atmospheric Research, but which is built by international community of climate scientists. So this is the temperature change that is projected by this model in the wintertime for the next 50 years. So 50 years from now, these are the types of changes in temperature that this model produces as a result of both the buildup of carbon dioxide and the natural variability that is not predictable. And you can see that we can get a range of outcomes here depending on the particular sequence of El Nino events, jet stream variability, etc. So we can have a world that actually has very little warming over the US and lots of warming over Canada, or we can have a world where the warming is more uniformly distributed over the continent. These are large changes. You can double this scale to get it into degrees Fahrenheit. So these are very large changes. And we have this range because of the natural variability. It's not because we don't know what we're doing. It's because we know that the natural variability can be large. Here is the picture for summer. Also can get a fairly wide range, something like more than 5 degrees Fahrenheit warming over much of the US, or we can get more muted warming over the US of only a couple of degrees Fahrenheit. And then I thought, since here I am at Scripps, I might pick out some more relevant local data for you from the climate model. So these are the summertime temperatures for California as a whole, as projected by this model. So what I'm showing you here are the observed, these are the observations at all of the stations in California over this 95-year period. So the average temperature for California as a whole in summer is 76 degrees Fahrenheit. And there have been summers that have been more than 2 degrees Celsius above that, roughly 4 degrees Fahrenheit, so sort of 80 degrees and down to 74. This is the average temperature for the summer as a whole. This is not a particular day, but the average over the 3-month summer. So if we look at what's in store, if we continue to build up our carbon dioxide concentrations, roughly 50, 60 years from now, this is what the climate model shows us. A mean warming of something like 7 degrees Fahrenheit, but a wide range. Some summers could be up to 11 degrees Fahrenheit warmer, or some could be only about 5 degrees Fahrenheit warmer. But the striking thing is that all summers will be warmer than any summer we have experienced in the last 95 years. So this is an enormous change. So even the coolest summer 50 years from now will be warmer than any summer that has been experienced by people in this room. And then finally, we can look at precipitation, and I'll show it to you in a slightly different format in terms of risk. So again, we have the human influence, we have the natural influence, so we can talk about risk in the future. So this is the risk of change in rainfall over the next 50 years. And let me help you read the graph. So these reds and orange colors, they're indicating that there's an better than 85% chance that the winters will be wetter in northern Canada 50 years from now than they are today. So that's a pretty good chance. You would probably bet money on it. We can look at California, Nevada, Oregon. better than 65% chance of drier winters. So note, it's not 100%, but it's more than 50%. So you might bet some money on it. You might plan for that. And then much of the eastern half of the US, actually it's 50-50. And in this case, the human influence on climate and the natural influence are about the same size, and so we have equal chances. So I'd like to leave you with our choices for the future and how we want to deal with this climate change problem. So in the world of climate science, we look at different scenarios for CO2 emissions, and we plug these into our models. And the community in this last report of the IPCC has considered 4 different pathways for fossil fuel emissions. The first is just continued growth, business as usual. A second one is where we reduce our emissions, but not until 2075. Another is where we reduce our emissions only 30 years from now. And then finally, where we take immediate action and reduce our emissions today. And in terms of the global temperature projections along those pathways, the continued growth projection, a warming of 7 degrees Fahrenheit for the globe as a whole. And you can contrast that now with if we reduce our emissions now, we can limit our warming to 2 degrees Fahrenheit. So 7 degrees Fahrenheit, what does that look like locally? So here's the map for the scenario where we continue a business as usual on our CO2 emissions. So 7 degrees Fahrenheit, 4 degrees Celsius for the global mean. But locally, it can be much larger. So over land, over much of the US, we're more like 5 degrees Celsius, or you can roughly double that to get Fahrenheit, so 10 degrees. And the Arctic, you notice enormous warming. And this has to do with the fact that as we warm the Arctic, the sea ice starts to melt. Then the open water absorbs a lot of sunlight, and that further melts the ice. And all of this amplifies the warming and then warms the air. So in conclusion, I just want to leave you with a schematic of this balance between human influence and natural influence. And on the human side, it's really the Keeling curve that we pay attention to. And on the natural side, it's this notion that the natural variability that causes our weather fluctuations and our climate fluctuations are largely unpredictable if we're looking 10 years ahead. And of course, as we look at more global scales, or we look farther in the future, then this scale starts to tip towards the human side and gives us a higher risk of climate catastrophes as we go in the future. Thank you very much. The question was, how does the carbon dioxide levels today compare with those in the geological past? So if we look back at the time of the ice ages, of course we had huge fluctuations in temperature and carbon dioxide. The levels that we're at now are beyond those. And in fact, during the ice ages, I think we're still trying to tease this out, but in fact, the warming actually produced the change in the CO2, not the other way around. So I think of it as actually a somewhat not analogous to the situation that we're in now. Right, so the question is what, we talk about reducing our carbon dioxide emissions, but what sort of percentage reductions do we need to have to do something meaningful? And I guess that's up to us what we consider meaningful. And if we can live with, warming of only a few degrees and what that means, how it plays out for the rest of the climate system, then that's our target. But certainly a world where the globally average temperature is 7 degrees Fahrenheit higher than it is today is an unprecedented world. I have a list of websites if you're interested in my presentation, and I could leave that, but there are many sources of information that can go into more detail to answer your question. Thank you for your question. The question is, can I talk more about the interaction between the sun and the earth? And I think you're asking the sun's influence on global climate. Certainly the sun does strengthen and weaken over time, but the changes that we've witnessed, the sun has not been a strong player. And one can also ask whether volcanic activity has contributed to the warming. And in fact, volcanic activity has actually been on the increase, and this causes a cooling of our climate system. So again, this long-term warming is very much a result of the greenhouse gas carbon dioxide buildup. So the question is, as other countries emit more and more carbon dioxide, is there a level of saturation in the atmosphere? That's a very good question. I think that the atmosphere is going to continue to be able to, CO2 will continue to rise in the atmosphere. But one thing I didn't talk about was that actually we only have the oceans and the land, plants, take up half of the CO2 that we are putting into the air. So if we didn't have that buffer of the oceans taking it up and the land, our CO2 in the atmosphere would be twice what it is, and we would have a lot more warming. We worry that as time goes on and as the oceans warm, their ability to take up carbon dioxide will diminish, and then more of the fraction of the CO2 that we're putting into the air will remain in the air. So it's kind of a not a good direction of the feedback there.
We're just about out of time. Please join me in thanking her for a wonderful presentation.